Okay, let's go back and pick up number 6 and then we'll finish up. It says 4 assembly lines can package in 10 hours. Then 2 assembly lines can package in how many hours? All right, so let's see, 2 assembly lines. So if I cut the assembly lines by half, or I divide by 2, then it should take double the time because I have less workers. And again, this is inversely related. I guess I thought this one had more details in it than what it does. So sorry about that. I could have just done it in order. So yeah, so if 4 assembly lines package in 10 hours and 2 assembly lines, so if I divide this by 2, this would double because they're inversely related. So not sure why I was worried about time on that one, right? Because I think there's one on the next review that's maybe more complicated. All right, prove that 0.9 repeating. And I know this bugs people, but a third plus a third plus a third is 1, correct? 3/3, make a whole. But if I convert these to decimal, these are all repeating decimals. And we would all agree that if you take 1 divided by 3, you get 0.33333 and so forth. So if I add these, I get 0.9 repeating. But, I mean, if these are all equal, because a third plus a third plus a third equals this, which equals this, then guess what? This guy has to equal 1. Okay, there's no option. So this, I'm not rounding, like this authentically is the same as 1. All right, so let's convert these to a fraction. So this one's terminating, so then it is on base 10, so tenths, hundredths, thousandths. Maybe I could scale it down by 2 because they're even. So this is what, 62, and this is what, 500. And then even again, so maybe I'll scale it down again and get 31 over 250. And it looks like, you know what I mean, that's kind of about all those guys have in common. You could use your divisibility rules a little bit here. So like add the digits if they're divisible by 3, right? Like add those up if it's divisible by 3. But again, 31 is actually prime, so we're okay. Now, repeating decimals, there's a couple ways to do this. One is, you could just know that 9s, 99s, 999s, all of those things give you repeating decimals, right? And so you could be like, okay, I need a repeating decimal in the hundredths position. So that's actually 99, because 15 out of 100 would be exactly 0.15. And it's that 99s, 9s, those are what give us those repeating. The other thing I could do is I could actually solve for that. So I could let n be 0.151515 dot. And because I want to move it 2 decimal places, I'm going to multiply by 100. And that's going to give me 15.151515. And your goal here is to have the decimals line up so that they cancel. So I'm going to subtract. And notice that's where that 99 comes in. And I get, what, 15. And so the repeating part goes away. And I get this. Now, I do need to simplify this here. So the rule, right, add the digits 6, 3 goes into both those because of the divisibility rule. So 5 over 33, okay? All right, here, so again, we kind of have, over here we have rational numbers. Irrational numbers are not nice square roots, pi, the E key on your calculator, those things. So this would be 3 radical 2, but again, this one's going to be irrational. It's not nice. Let's see. Square root of 14 is actually nice. That's not a problem. Pi is also irrational. It goes forever and never ends. So this one's going to be irrational as well. Okay, so everything else is rational. Now, it might be in some other groups too. So our counting numbers are natural numbers like 1, 2, 3, 4, 5. They go forever. Then we add 0, which is whole numbers. Then we add nice positive and negative numbers, which are integers. And then we add our fractions. And again, decimals, and they could be repeating decimals or just terminating decimals. That doesn't matter, okay? So either one, because both of those can be turned into fractions. So this one is an integer, and it belongs to everything bigger. So integers, rational, and then real numbers are the big, like the universe. So integers, and then rational, and this would become part of real. 3/4 is a fraction, so again, it's not an integer, but it would be a rational number because ratio and real. 0 is a whole number, so it belongs whole numbers and everything bigger, so that would be whole numbers. and then what? Integers, and then rationals and reals. So we just kind of keep adding numbers as we need them. All right, real. And then 4 is actually a natural number, like 1, 2, 3, 4, 5, 6, 7. And then, so this belongs to everything on this side. So this is going to be natural, whole, integer, rational, and then real. Okay, there are imaginary numbers that are kind of like their own little universe, but this is kind of our universe of numbers. And we have rational ones, which can be written as a fraction or a decimal, but ratio means fraction. And then we have irrational. So most of these, other than square roots that go on forever, pi and the e, those are numbers that never end, but they don't have a pattern. But if you're a repeating decimal or fraction, all of these can be written as a ratio. And so that's why they're rational. So if you're like, well, what about -6? Well, stick a 1 under it. What about 0? Stick a 1 under it. You know, what about 4? Put a 1 under it. You can always make those into fractions, right? All right, and then let's look at the last page. All right, let's look at this one. So I'm going to put the first number in the house, the other one out here. Put your decimal. For some reason, I did this earlier. I put an extra 0 in there. I don't know why. So 16 doesn't go to 7, so that's why I know I have a decimal. So I'm going to take it times 4. Again, 16 times 4. If you need scratch paper, that's great. Otherwise, it's 64, which is 6. I'm going to bring down a 0. I get 60. 16 times 3 is what? 48. So I get 12, and then let's see, I bring down another 0, and then 16 times, okay, I don't know, let's see, 16 times 7 is what? 2, 4, 7, 8, 9, 10, 11. That looks actually pretty good. So I'm going to put 7 up there, 112, get 8, and then bring down another 0, and finally I get my 5, which is 80, and I finally get to 0. So I know that this guy is a terminating decimal, and I knew that to begin with, because if I do prime factorization, the top is 7. I get 2 times 2 times 2 times 2. If your denominator, after you simplify, like if anything cancels, cancel, but do you see how if it's only 2s or 5s, you can make it into like a 10, 100, 1,000, or whatever. I just have to scale this up by what, a 5, 5, 5, 5 to scale it up, right? So like, you know, to get it into this place value. And if you do that, you'll actually get this. I mean, I can show you guys that. But if I times 5 times 5 times 5 times 5 to scale this up so that I actually get, you know, thousands, 10,000s, whatever. If I take 7 times 5 times 5 times 5, how many of them? 4 of them? Do you see how I get this? Right? Which is this, right? And then my denominator would be tenths, hundredths, thousandths, 100,000s. So, I mean, if I take that, I'm going to have this number over 100,000. So you can, if you have only 2s and 5s, you can scale it to get it in base 10. Okay. So I know this is going to be terminating because it's all 2s here. All right. Let's look, 14 over 15. So again, first number goes in the house, second one out here. And again, you know it's less than 1, so you might as well add 15 out of 15 is 1. So let's go ahead and add that. Let's see, I don't know if 9's going to do it. Let's look at 8. 40, that would be 8, 9, 10, 11, 12. So maybe I can do, oops, I don't know why. What am I doing here? Yeah, 15 times 9. Sorry, trying to rush here. 45, 9, 10, 11, 12, 13. All right, that's a little better. So I guess 9 works. 135. I get 5. Bring down a 0. 3 is 45. Bring down a 0. 3 is 45. Get 5. Bring down a 0. I get 3. Okay, so it looks like obviously I'm going to have a repeating decimal here, right? And you shouldn't be surprised. So this is 0.9, just the 3's repeating, not all of it. So only line here. This should not surprise you. If you look at the denominator, and again, you could factor the numerator too to make sure, are you okay? This is 2s and 7s, nothing's going to cancel. But if you look at the prime factorization, I can make this guy into a 10, but I can't scale up to get rid of a 3. Like there's nothing you can multiply a 3 by to make it a 10. So I know that this is going to be, because of this 3, I know it's going to be a repeating decimal. 2s and 5s in your denominator are great. You can use base 10, but any other number except 2s and 5s, you cannot convert them into 10s. And so you can't scale up to ever get rid of that 3. So it's going to be repeating. All right, and then let's look at the last 2. Write a story problem that can be solved with a strip diagram, solve it with a strip diagram, and with a proportion. So I could be, let's see, let's see, I'm going to pause a second and think so that I don't take up all the time. I'll be right back. Okay, let's look at this one. If I plant 3 flowery plants for every 2 leafy plants in my garden, or I plant, sorry, not if. If I plant 12 flowering plants, how many leafy plants would I use? How many plants total? So I'm going to draw I have my little flowery plants. I do 3 of them. For my leafy plants, I do 2. You can tell I'm ready for spring here, right? And it says I have 12 flowering plants. So if this is worth 12, I know that each strip is worth 4, because 4 times 3 is 12, which means every strip is worth 4. So that means I would plant 8 leafy plants. And then I can also see the total, because if I have 12 and 8, then that would mean that there's 20 plants total. These are my flowering ones. All right, and then the second way is with a proportion. So if I have 3 flower to 2 leafy, so this is flower to leafy, then I would have 12 flowering would go on top. So I have 12 flowering to leafy, so 12 to leafy. Now again, this isn't going to give me my total though. You can cross multiply. So 3L equals 24, divide by 3, divide by 3. Leafy is 8, okay? And that would be 8 leafy. And then at this point, to get the total, you could just add to get 20. The other thing is you could redo your proportion. So I could say there are 2 leafy out of 5 total, because if there's 2 parts to 3 parts, there's 5 total parts. And then I could do, so I have leafy to that, and then leafy, do I know leafy? Well, I do now, I guess I could do that. Leafy to total, or I could do flowery 3 to 5, and then the 12 to total. And then again, if I cross multiply, I get 20 total. So plants, okay? Otherwise, you could just add. All right, hopefully that helps. And I will chat with you soon.